The Very Large Telescope finished construction in the year 2000, although that sentence is a little misleading on two different levels. The first is that the VLT isn't just a single mirror telescope. A misleading name then? Maybe. Let's see why it's still only considered one telescope. Initial designs had it as a limited array of 4 behemoth telescopes, 25 m tall each, with mirrors stretching 8.2 m across. These were called unit telescopes, and they could work independently at studying the stars. Each one is capable of an angular resolution of 50 ms, which is good enough to see details. Smaller than a DVD on the International Space Station. The second level is that the VLT is constantly evolving. In some sense, it is not finished even now. In 2004 and 2007, a total of 4 new auxiliary telescopes were added to the VLT's array. Each of these auxiliaries has a smaller mirror only 1.8 m across. Additional instruments have been routinely added over the years, some as recently as 2018. There are 16 currently in operation, ranging from spectrometers to infrared images, with more to come in the future, such as Foremost, which is an upgrade to the Vista telescope, instrument that is also part of the VLT site. Such a massive array can be difficult. VLT mirrors are exposed to the open air each night. The Atacama Desert in northern Chile, where it's situated, may be ideally suited for observations. It hasn't rained there since records began, but dust can sometimes blow in. Every 18 months, the mirrors must be delicately washed with chemicals designed to remove their aluminium coating, and then a new one is applied. This process does not need very much aluminium. Only about 12 G is used to coat an entire 8 m mirror, less than the amount used in a drinks can. This is because the aluminium is coated on the mirror about 80 nanometers thick. Each unit telescope is a pristine feat of engineering. The 430-ton structures are each about the weight of a jumbo jet, and yet they so perfectly balanced on their hydrostatic oil film bearings that they can be rotated by hand. The mirrors are so precise. If you scaled them up to the size of the whole Earth, the imperfections on them would be smaller than a pebble. But the truly impressive feats are still to come. As powerful as each unit telescope is on its own, it is when they work together that they can act as one telescope. Let's talk about the telescope's technique known as interferometry. Light travels in waves, and when you combine 2 waves just right, their peaks can amplify each other. Underneath the VLT, there are a series of tunnels, lined with mirrors in complex configurations. Light from the various telescopes is fed into them. They are placed with accuracy down to a fraction of a wavelength to ensure the light enters in just the right phase so that everything lines up. In this way, a greater resolution of detail can be gained. An individual unit telescope can see objects that are 4 billion times fainter than what you can see with the naked eye. When interferometry is brought to bear, this becomes 25 times more effective. It should be noted that the amplified waves of light do have some drawbacks. Light as it bounces around all these mirrors can get lost. The process is not very efficient. As a result, the object the VLT is looking at needs to be quite bright to begin with. Secondly, interferometry does not naturally create full images, instead merely picking out certain details and features of what is visible in what are called fringes. However, this is often enough for astronomers' purposes. And if a more detailed image is required, the VLT's observational data can be processed into crisper, full images. It just takes more time and processing power. The VLT's effective 200 m diameter virtual mirror provides excellent resolution, but that's not to say that it's able to pick up the same quantity of light as even the 30 m mirrors. Obviously, there is a lot of empty space between the units that is not covered by mirrors. They are not picking up any light. But what it does perceive is revolutionary. Ranging from the beautiful, like this eye-catching look at the galaxy NGC 1398, to the groundbreaking, like this first ever image taken of an exoplanet, VLT is often on the forefront of discovery, are normally only seen through the absorption of light traveling through their atmospheres, or the slight dimming of any stars they pass in front of. It's rare to see an actual photograph of one. And yet, in 2004, the VLT captured this image of 2M1207b, a Jupiter-like planet, that is, located 230 light-years away from us in the Hydra constellation. This image was taken with the aid of NACO, the Nasmyth Adaptive Optics System, which has since been replaced by the more advanced optics system known as NAOMI, the new adaptive optics module for interferometry, which, according to the ESO website, is putting the VLT's interferometry on steroids. It's worth noting, adaptive optics is a vital part of ground-based telescopes. Movement in the atmosphere can cause distortions in the light arriving at the telescope from distant stars. This can make it much harder to make out detail and is the main advantage of space telescopes over ground ones. In space, you don't have to compete with the atmosphere between you and the object you're observing. However, the VLT's adaptive optics showcase an ingenious solution to this problem. By using guide stars or lasers, if no suitable star can be found, the VLT can track the distortion taking place as a result of the atmosphere by seeing how the light from these guides differs from what it should be. Then, using actuators under the mirrors of the unit telescopes themselves, the VLT causes tiny distortions in real time in the mirror to counteract the distortion in the air. This can negate much of the negative effects of the atmosphere, granting the VLT a much better look at the universe. So, let's talk about some of the VLT's discoveries. With so much data to choose from, it's really about picking my favorites. The VLT has looked at the aftermath of colliding neutron stars, detecting for the first time the freshly made heavy element strontium, an element used in fireworks. It has measured the temperature of the distant universe by detecting carbon monoxide atoms, confirming that 11 billion years ago, space was slightly warmer than it is now, minus 264 degrees Celsius versus minus 270 degrees Celsius. So admittedly, still quite chilly. But perhaps the most exciting discoveries of the VLT was its role in helping prove the theory of general relativity, which earned Reinhard Genzel the Nobel Prize for Physics in 2020, as well as confirming the existence of the monstrous black hole at the center of our galaxy. Einstein's theory of relativity had long predicted the existence of black holes, as shown by Karl Schwarzschild in 1619. For decades, though, scientists wondered whether these universe-warping objects actually existed. A mathematical physicist named Roger Penrose went on to prove in his 1965 paper Gravitational Collapse and Space-Time Singularities that black holes were not just mathematical artifacts in Einstein's theory, but concrete certainties. It was inevitable that they could and would form, but still, it took until the turn of the millennium before the first black hole was confirmed. During this time, scientists began to suspect that there was one such black hole at the center of our own galaxy. Signals had been detected coming from the center of Sagittarius, 25,640 light-years away, as far back as 1931. In 1971, two radio astronomers, Bruce Bollock and Robert Brown, noticed a bright, compact object at our galaxy's center that gained the name Sagittarius A star. But telescopes were not powerful enough to truly peer into the heart of Sagittarius A star to confirm what it was. This changed with Andrea Ghez and Reinhard Genzel in the 1990s. Through detailed observations that spanned nearly 30 years, each astronomer began to map out the motion of stars in the center of Sagittarius to see how they interacted with Sagittarius A star. General relativity predicted rapid movement of any star moving past the black hole. However, it also predicted precession, a change in the orbital path over time in the direction of the star motion, rather than looking like a circle or an ellipse, a star showing such precession would travel the path of a evaluation of the stars around Sagittarius A star for multiple orbits, and each orbit could last up to 16 years. So decades of observation were needed to confirm Einstein's theory. And fortunately, telescopes like the VLT were by this point available for use. Genzel's team made use of the VLT to watch the motion of the stars around Sagittarius A star, while Ghez made use of the Keck Observatory in Hawaii to do the same. Together, they were able to confirm this precession was indeed taking place. As further evidence, in 2018, the VLT observed star S2 traveling around Sagittarius A star at 7,650 kilometers a second, or 2.55% the speed of light, exactly in line with the speeds Einstein had predicted. This finally confirmed Sagittarius A star's identity as a supermassive black hole. Thus, in 2020, Ghez and Genzel both received the Nobel Prize of Physics for the discovery of a supermassive compact object at the center of our galaxy, and Roger Penrose, who had first proved mathematically that black holes inevitably arose out of Einstein's theories, received a Nobel Prize for the same. So, there you have it. The VLT has been massively influential up until this point, providing data for countless scientific papers and placing itself as one of the most productive telescopes mankind has yet produced. But going forward, in an era where extremely large telescopes begin to be more common, and as telescopes like the James Webb Space Telescope orbit in our skies, the VLT will need to up its game to stay relevant. It will need to evolve, with its instruments continuing to be updated and modified. The VLT still has the potential for years more of valuable contribution to the scientific community. Astronomers will need to think carefully about how this is best achieved, but it should not be too difficult. The VLT is a powerhouse. I'm certain it will continue to find its niche for years to come. So, were you already familiar with the VLT? Would you like to hear more about VLT and its discoveries? Let me know in the comments below. When building the VLT, it was important for engineers to use the greatest levels of precision. If they tried to rotate the 430-ton telescope and something had been misaligned, it could have caused hidden damage that might not have been immediately detected.